Welcome back to Very Ordinary Differential Equations. In this lecture, we take some of our power series techniques and see some interesting things we can do by applying them to second-order Euler equations. So we've already studied second-order Euler equations. These were differential equations of the form x squared y double prime plus axy prime plus by equals 0. Presuming that x to the alpha was a solution, we found that alpha had to solve a quadratic equation, alpha squared plus a minus 1 alpha plus b equals 0. When this quadratic equation had two distinct real roots, then x to each of those powers formed a fundamental set of solutions. When that quadratic had a single real root, a fundamental set of solutions was given by x to the alpha and x to the alpha log x. And finally, when there was a complex conjugate pair of roots, lambda plus or minus omega I, then a fundamental set of solutions was given by x to the lambda times either the cosine or the sine of omega log x. So now let's see how our power series techniques can interact with these equations, and then we're going to derive some interesting things. So here was our second order Euler equation. Notice that x equals 0 is absolutely a singular point of this equation, since it's a root of the leading coefficient x squared. So rather than centering our power series somewhere else, however, we're going to just change the form of our differential equation, presuming that instead this Euler equation is of the form x plus 1 squared y double prime plus ax plus 1 y prime plus by. This will allow us to essentially change the center of the Euler equation rather than the center of our power series. Now we can center our power series at the ordinary point x equals 0. So here is this Euler equation that we've recentered. We expand everything out, and now we can presume that our solution y is a power series centered at 0. After a rather lengthy amount of manipulation, we have this power series for y. We can multiply a derivative by a constant or by ax, or we can take two derivatives, multiply by x squared, and recombine. So taking all of the techniques that we've learned, we'll end up with this. So here is now one large power series that represents this differential equation, which is set equal to 0. And as we have seen several times now, therefore every coefficient must be equal to 0. So the differential equation was this recentered second-order Euler equation. Already known techniques tell us that x plus 1 to the alpha is a solution, provided that alpha solves this quadratic right here. So if we want to force x plus 1 to the alpha to be a solution for a specific choice, we're going to choose an alpha and say we want that to be a solution. We can just pick capital A and capital B appropriately so that our desired choice of alpha will indeed solve this. Then we can use the recurrence relation above, generated by the coefficients of our power series, and that will help us find a power series representation for the solution. Therefore, we'll have found a power series representation for what we assumed was going to be a solution, x plus 1 to the alpha. So y equals x plus 1 to the alpha is going to be a solution, provided alpha times alpha minus 1 times a alpha plus b is 0. We are picking a and b to make this happen. So one way we can force it to happen, not the only way, but still one way, is just suppose a is 0 and b is alpha times 1 minus alpha. Then we will have alpha alpha minus 1 plus 0, alpha 1 minus alpha. Everything cancels out, and we really will get 0. We can also set our initial conditions to be y of 0 is 1 and y prime of 0 is alpha. So with this in mind, the recurrence relation is now given as follows. Since we have fixed a equals 0, and b to be alpha times 1 minus alpha, here's our b, and anywhere we had a capital A has just vanished because a was set to be equal to 0. So this is now a recurrence relation that helps us find a sub I for larger and larger indices. Solving for a sub I plus 2 will generate this. So we simply need to take these two terms, move them to the other side, and that's where this minus sign comes from, then divide by I plus 2 and also divide by I plus 1. The initial conditions were that a sub 0 equals 1 and a sub 1 equals alpha. And with this recurrence relation and two initial values given, we can generate more and more terms. So here was our recurrence relation with our initial conditions. As the simplest case, let's go ahead and suppose we want alpha to be 1. So we're trying to find a power series representation for the incredibly complicated function x plus 1 to the first. Alpha is just 1. Well, with alpha set equal to 1, this term is going to vanish, and also a1 is just 1. So our recurrence relation simplifies a little bit, and our initial conditions are just that a0 and a1 are both equal to 1. So here is our simplified recurrence relation and initial conditions when we want to force alpha equal to 1. Then what we can find is that a sub 2 must be 0. Okay, by plugging in I equals 0, you get a 0 here, you get a 0 here. Overall, a sub 2 is 0. A sub 3, if I let I equal 1, well, notice that here I end up with a 0, but if I equals 1, we get an a sub 2, and we already know that a sub 2 is 0. So in fact, a sub 3 is also going to be 0. But look at our recurrence relation. If both of these terms are 0, then regardless of the value of I, if both of these are 0, this whole thing will be 0. So if there are ever two consecutive a sub i's which are both 0, then the next one will be 0, and the next one, and the next one, and so forth. And since we have found that a sub 2 and a sub 3 are both 0, then we have found that every a sub I after this point will also be 0. So we found that a0 is 1 and a1 is 1, and every single other a sub I is 0. So the power series representation for x plus 1 to the alpha, where alpha is 1, so x plus 1 to the first, well, a0 is 1, a1 is 1, and every other coefficient is 0. In other words, x plus 1 to the first is just 1 plus x. Of course it is. X plus 1 to the first is 1 plus x. Thankfully, we actually were able to derive something that was obviously true. We're going to work through three similar examples, getting a little bit more complicated every time. So as an example, let's let alpha be 3. So we have a predetermined solution of x plus 1 to the alpha, or x plus 1 cubed. This will satisfy that y of 0 is 1 and y prime of 0 is 3. So we make our choice that a is 0 and capital B is alpha times 1 minus alpha. This works out to be minus 6. So then the recurrence relation becomes as follows. Here is our alpha times 1 minus alpha, and with capital A being 0, any term that had that in it vanished. So now we can find a sub 2. By setting I equals 0, this vanishes here, this vanishes there. Okay, however, we do have this minus 6 hanging around, so not everything vanished. We work out a sub 2 is 3. Then by letting I equal 1, we will find that a sub 3 is 1. Okay, so just by using this recurrence relation, by setting I equals 0, we got a sub 2 to be in terms of a sub 1 and a sub 0, which worked out to be a sub 2 equals 3. By letting I equals 1, we got a sub 3 expressed in terms of a2 and a1. Working through all of these values, we got that a sub 3 is 1. So having found a sub 2 is 3 and a sub 3 is 1, we continue to use this recurrence relation. A sub 4, by setting I equals 2, we get 2 times 2 times 3, a3, there it is. 2 times 1 minus 6, a2, there that is, and 4 and a 3. So 12a3 minus 4a2 over 12, with a minus sign out in front. However, since a sub 3 was 1 and a sub 2 was 3, this numerator works out to be 0. So a sub 4 is just 0. And for a sub 5, by letting I equals 3, we plug that in, compute all of these things here. Works out to just be 18a4 over 20, but we just computed that a4 is 0, so a sub 5 is also 0. But look what we now have. Two consecutive a sub i's, a sub 4 and a sub 5, are both 0, meaning a sub 6 is going to be 0, a sub 7, and so forth, all going to be 0. So since we have two consecutive a sub i's which are 0, everything after that point is as well. So the only a sub i's that aren't 0 are the ones we already found. Therefore, x plus 1 cubed has this power series representation, but a sub 0, a1, a2, a3 are not 0, but everything after that point is. So we have found 1 for a sub 0, 3 for a sub 1. We then use the recurrence relation to find 3 for a sub 2 and 1 for a sub 3. So here were our initial conditions of 1 and 3. Here are the 3 and the 1 that we computed, and then everything after this point is 0. In other words, the power series for x plus 1 cubed is just 1 plus 3x plus 3x squared plus x cubed, and then all zeros, which is exactly what you would get if you simply expanded this out by hand. Now, as a second example, let's let alpha be minus 1. So y equals x plus 1 to the alpha is our known solution. Therefore, I can easily compute that y of 0 is 1. And by taking a derivative and plugging in x equals 0, we can compute that y prime of 0 is minus 1. So setting alpha equals minus 1 turns our recurrence relation into this formula right here. Here is your alpha times 1 minus alpha, minus 2. So there's the recurrence relation we get. In this case, we're going to be a little clever in how we work with it. That I times I minus 1 minus 2, up in the numerator here, expands as I squared minus I minus 2, which then factors as I plus 1 times I minus 2. Meaning here we're going to have a factor of I plus 1 with a factor of I plus 1 and a factor of I plus 1. That's all going to cancel out. So if I cancel that shared factor of I plus 1 from every term, our recurrence relation becomes a little more manageable. Okay, so here is the simplified recurrence relation that we were able to figure out in the specific case of alpha equals minus 1. Here's our simplified recurrence relation, and now we can start computing some terms. So by setting I equals 0, we get that a sub 2 must be 1. By setting I equals 1 and using our known value of a sub 2, we get that a sub 3 must be minus 1. So we have found that a sub 2 is 1 and a sub 3 is minus 1. Our initial conditions were a 1 and a minus 1. So far a sub I are 1, minus 1, 1, minus 1. It seems to just be negative 1 to the ith power, alternating between 1 and minus 1. This definitely holds for I equals 0, 1, 2, and 3, the ones that we found. So let's assume that it does hold for all indices up to some k plus 1. Then the recurrence relation would give a sub k plus 2 is negative 2k ak plus 1 plus k minus 2 ak over k plus 2. This was our recurrence relation. If I assume that ak plus 1 is negative 1 to the k plus 1, and I assume that ak is negative 1 to the k, we're hoping that all of this will simplify down to negative 1 to the k plus 2, matching the desired format for the next coefficient a sub k plus 2. So we're trying to do an inductive proof that indeed a sub I is always negative 1 to the I. So now we just have to simplify all of this. Distributing this minus 1 across the numerator gives me a negative 2k here, and I'm going to increase this negative 1 to the k to make it negative 1 to the k plus 1. So distributing this minus sign, I left this power of minus 1 alone, and I increased this one. So this 2k now has a negative out in front, but this power became k plus 1. The objective here is now I have the same power of minus 1, I'm going to be able to factor that out. So here's what we have so far. Once we factor out that shared negative 1 to the k plus 1, our numerator is negative 2k plus k minus 2. In other words, this numerator is just negative 1 times k plus 2. Negative 2k plus k is just minus k. So I get a minus k minus 2, I factor that minus out, and it's just k plus 2. K plus 2 cancels k plus 2. This is just negative 1. This negative 1 now can be absorbed to increase this power by 1, and indeed, we have found that a sub k plus 2 is in fact negative 1 to the k plus 2. So we have inductively proved that the a sub i's really are just negative 1 to the I. So having proven that a sub I is just negative 1 to the I for every I, the power series for x plus 1 to the minus first is just the sum of ai x to the I, where a sub I has this known form now. In other words, it's just the plain old geometric series. This is just negative x to the I This is a geometric series where the common ratio is minus x, and we already know that converges to 1 over 1 minus that common ratio. And 1 minus minus x is indeed 1 plus x. So 1 over 1 plus x is exactly this series here. So using power series, we were actually able to re-derive that a geometric series converges as we hope. As our third and final example, let's get a little tricky. Let's let alpha be negative 1/2. So x plus 1 to the negative 1/2 power is our known solution. In other words, 1 over the square root of x plus 1. Computing y of 0 gives me a sub 0 is 1. Taking a derivative of this and plugging in x equals 0 gives me that a sub 1 is minus 1/2. Also, with alpha being minus 1/2, when I compute alpha times 1 minus alpha, we get negative 3/4 here. So here's our recurrence relation. It's a fraction with a fraction up there in the numerator. Also, our initial conditions did generate a non-integer value right here. We're going to simplify that numerator a bit. Okay, I'm going to put that 4 down in the denominator. However, I do then have to multiply this by 4 to make it work out. And now I just start computing successive a sub i's. We know that a sub 0 is 1. And we know that a sub 1 is minus 1/2, and now I can just start computing. A sub 2, for example, works out to be positive 3/8. So now we have a sub 0 is 1, a sub 1 is minus 1/2, a sub 2 is positive 3/8. Continuing to use the recursive formula, we're going to get that a sub 3 is minus 15/48. A sub 4 is positive 105/384. So here are the a sub i's that we've computed so far. It's not immediately obvious what the pattern is. However, notice that in the numerator, I went from 1 to 3 times 5 to get 15 times 7 to get 105. In the denominator, I went from a denominator of 1 times 2 times 4 times 6 times 8. So the numerator appears to be a product of consecutive odd numbers, and the denominator appears to be a product of consecutive even numbers. They definitely also alternate sign. And we have this product of odd numbers making the numerators and product of even numbers making the denominators. So altogether, maybe we can come up with a good conjecture about what a sub I in general will be equal to. Here we have it. We want the a sub I to alternate negative 1 to the I, a product of odd numbers over a product of even numbers. Okay. Now, I want this formula to hold for every I. The trouble is, for I equals 0, we would end up with a negative 1 double factorial, which doesn't even exist. Okay. We're just going to therefore manually declare a sub 0 is 1 because it was given to us. Everything else should match this formula here. Now this formula does match our computed values for a sub 1, a sub 2, a sub 3, and a sub 4 that we figured out so far. So all we need to do is verify that the recurrence relation preserves this formula. We have more than enough base cases already computed. So here was our conjecture. Here was our recurrence relation. So if I take this form for ai plus 1, we would get negative 1 to the I plus 1. 2 times I plus 1 minus 1 works out to be 2i plus 1. 2 times I plus 1 is 2i plus 2. So here's what the formula would predict for a sub I plus 1. Here's what the formula predicts for a sub I. So overall, all of this is what we have for a sub I plus 2. We just need to now simplify this and hopefully end up with what this formula up here would predict for a sub I plus 2. Now, one thing that we can account for are the powers of minus 1. Negative 1 to the I plus 1 is the opposite of the next power of minus 1. Remember, powers of minus 1 just flop back and forth, plus 1, minus 1, plus 1, minus 1. So whatever this one is, I don't know if this is plus 1 or minus 1, but it's definitely the opposite of the one that comes next. Whereas this one, whether it's plus 1 or minus 1, it is the same as what comes 2 steps later. Okay, we're also going to go ahead and simplify that occurrence of 4i, I minus 1, minus 3. Once you expand that out, it does factor as 2i minus 3 times 2i plus 1. So overall, we have managed to change both of our powers of minus 1 to be minus 1 to the I plus 2, okay, using what was on the slide before, that negative 1 to the I plus 1 is simply negative 1 to the I plus 2, and negative 1 to the I is just the same as negative 1 to the I plus 2. Okay, and here is our factoring of 4i, I minus 1, minus 3. It's just 2i minus 3, 2i plus 1. All right, we factor out the negative 1 to the I plus 2. We made every occurrence of negative 1 to a power be the power we were hoping to get. Our desired formula for ai plus 2 should have a negative 1 to the I plus 2 hanging out. So factor that out, and now we can turn our attention just to simplifying this enormous mess here. Also, both terms have been adjusted to have 2i plus 2 double factorial. So up here we had 2i. This is the product of 2i, 2i minus 2, and so forth. If I multiply it by 2i plus 2, the next even number, I would get this double factorial, so I also introduce it up here in the numerator. So if I were to cancel this out from this last term, what would be left were all of these even numbers. And the purpose of doing that manipulation is exactly to make both of these denominators look the same. Now I can take this shared denominator of 2i plus 2 double factorial and just express it down in the denominator. Once I do that, things are starting to look slightly simpler. So I've moved that 2i plus 2 double factorial down in the denominator, and now we just have all of this up in the numerator. Also remember that this power of minus 1 is exactly what we wanted, and it's already hanging off on the left factored out, so very much leave this alone. Okay, doing some more work in the numerator, okay, and in the denominator as well. So this 8i, if I take a 2 out of it, I get a 4i times 2, and then I take that 2 and I distribute it in here. So instead of 8i, I call this 4i times 2, and I put the 2 in here. So I get 4i times 2i plus 2. Also, this 2i plus 1 double factorial is a product of a bunch of odd numbers. Pull out this largest one and then say, here's the product of all the odd numbers after that. Okay. Down in the denominator, we've done something fairly similar. This 2i plus 2 double factorial, if I multiply the next even number, I can absorb these two things together as just 2i plus 4 double factorial. Now there's a shared factor of 2i plus 2 occurring here, here, and down here. So we can cancel that out. All right, slightly simpler. Here's where we are so far. In our expression for a sub I plus 2, we already have the exact power of minus 1 we want on the left, negative 1 to the I plus 2. We're just hoping to get all of this to reduce down to certain double factorials in a ratio. All right, so first things first, this odd number times the product of all the odd numbers after it can be expressed as the product of all the odd numbers up to 2i plus 1, and I can do that here as well. Okay, so the product of all these odd numbers times the next one will be the product of all the odd numbers up to and including 2i plus 1. Now, I have a shared factor of 2i plus 1 double factorial, so I will have 4i minus 2i plus 3. Overall, 2i plus 3 times that double factorial. Down in the denominator, instead of calling this 2i plus 4 double factorial, within this parenthesis, just call that 2i plus 2. So down here I have 2i plus 2 double factorial, but now up in the numerator we figured a 2i plus 3 times this product of a bunch of odd numbers. But this is now a product of all the odd numbers up to 2i plus 1 times the next one. Absorb that into a single double factorial. Now, 2i plus 3 can be written as 2 times I plus 2 minus 1. Overall, what do we now have? ai plus 2, this index is now I plus 2, has been written as negative 1 to that power, 2 times the index minus 1 double factorial over 2 times the index double factorial. This is exactly the form we wanted. So what we have determined is that other than a sub 0 being just manually forced to be 1, all of the other a sub i's we've inductively proved follow this formula. A sub I is always -1 to the index power 2 index minus 1 double factorial over 2 index double factorial. Therefore, our known solution of 1 over root x plus 1 can be written as a sub 0 hanging off by itself plus all the other terms beginning at index 1 and going on, a sub I, following the formula that we've proven holds, x to the I. And this is the traditional Taylor series for the function 1 over root x plus 1 centered at x equals 0. So again, using power series techniques, we have shown that a power series representation for a certain power of 1 plus x, specifically 1 plus x to the minus 1/2 power, is exactly the Taylor series that we could have found. Altogether, what was the point here? We didn't really learn any new techniques in this section. Rather, what we did is we set up a differential equation with an already known solution, 1 plus x to the power alpha, for a specific choice of alpha. Then that function will be equal to its Taylor series centered at 0. Representing the solution as a power series will then be the Taylor series for the function. So the recursive formula for the coefficients that we get using our power series techniques corresponds to a recursive formula for the higher derivatives of the function. On the one hand, we used power series to solve a differential equation. We got a recursive formula for the coefficients. If you were just finding a Taylor series for the function, you'd be computing higher and higher derivatives. And you would also end up with a sort of recursive looking formula for the derivatives of these particular functions that we had. So there is definitely a relationship to be found between this power series approach and the Taylor series approach.